Hello everyone, I hope you are doing well. So in today's video, I'm actually going to go through the Section B VCE Physics sample paper, short answer questions. So yeah, let's get started because I just want to finish this paper. Let's just do it. Okay, the mass of a planet Mars is this. The radius of Mars is this. The universal gravitational constant is this. Calculate the acceleration due to gravity at the surface of Mars. Very nice and easy question. That'll be G is equal to G m r squared, where our G in this case is 6.67 times 10 to the negative 11. Your mass is 6.4 times 10 to the power 23 all over your radius, which is 3.4 times 10 to the power of 6 and all squared. Okay, that will give us 6.7 11 6.4 23 3.4 squared. That will give us 3.7 as your answer. Very nice. A probe of mass 0.2 kilogram is released from a height of 10 meters above the surface of Mars. Assuming that the gravitational field strength is uniform, the same at the surface, so it's still 3.7, sketch the gravitational potential energy of the probe as a function of height above the surface of Mars on the axis provided below, and below this as UG. Take potential energy at the surface of Mars is 0. If the height, so the energy must be 0. At the surface of Mars is 0, include the initial potential energy value of the energy axis. On the same axis, sketch the kinetic energy of the probe and label this as EK. Okay, because we know that your potential energy, your gravitational potential energy, PE, your potential, just let me write it nicely. So your potential energy is equal to mgh, where it's pretty much proportional to h. So if height increase, so if h is 0, energy is 0. What about if I want to find when it's 10? So potential energy when the mass is 0.2, gravitational is 3.7, and your height is 10. So I want to find that. So what's that gonna? So doing that, 0.2 times 3.7 times 10. That's 7.4. So here will be 7.4. Right over here. Somewhere around here. Okay. That's alright. And then let me just find another point. Let's say 5. So PE 0.2, 3.7, 5. That will give 3.7. So 3.7 is right over here. So it's a nice linear line. Somewhere like that. So perfect. And let's label that as UG. UG. And we also want to include the initial potential energy values. So this is 0, 0. What do we know about the kinetic energy? Because imagine that this probe, if I draw the planet, imagine that this probe is like on top over here. And this is 10 meters. This is where it's max. What's happening? Well, it starts off at, if you think about it, it starts at 0. Imagine it starts at 0, height is 0. What's happening to that energy? If all that energy is gone, like the potential energy is all gone. Well, it's all going to be converted to kinetic energy. So it means, what does that mean? Well, let's use a different color. So when the energy, the UG, so your actual potential energy is 0, that's where your kinetic energy is at max. So it would still have the same thing. So the same energy. And when it's at 10 meters, that's when your potential energy is at max, but your kinetic energy is 0. So that'll be over here. So you pretty much will have a graph that looks similar like this. Perfect. And we can call that EK. So pretty much, that's how it is. Okay. and this point here is 0. So if I write this would be 0. Writing the point again, so it's 0.2 times 3.7 times 10, 7.4. So this is 7.4. Yeah, that's your answer for that one. Perfect. It's not too bad. Yeah. All right. Question 2. Figure 1 shows a part of a particle accelerator. Electrons are accelerated by a voltage of 10,000 volts in an electrical gun, consisting of 2 plates that are 0.1 meters apart. After exiting the gun, the electrons pass into a region of uniform magnetic field of strength 0.02 Tesla directed into the page. Ignore relativistic effects. So we have the mass of electrical charge and the strength. Give the strength of the electrical field between the plates. Okay, so I'm going to go on my formula sheet. You should have a formula for that. So that is... okay, this is the formula that I have. So it's V equals ED. And we want to find E, the electrical field. So it's E equals V over D, which is your voltage, which is 10 volts, all over your distance, which is 0.10. So doing that, so 10,000 volts over 0.1, that gives you 100,000, so pretty much. And we want to include the appropriate unit. So what I'm going to do is, well, it's all in 2 significant figures. So I'm going to write as 1.0 times 10 to the power of 1, 2, 3, 4, 5. And because it's volts divided by this, so it's volts per meter, -1. Yeah, so that's the answer for that one. Calculate the speed of the electron as they exit the electron gun. So the formula for that is half mv squared equals qv. Okay, so we want the v, the velocity. So it is v squared. So v squared is equal to 2qv over m. So v is the square root of 2qv all over m. So let me just rub this all away. And this is all we're going to need. This formula right over here. Just going to put it over here. So, okay. Let's write all of the stuff. So, 2, what's the charge? Well, the charge of the electron is negative 1.6. So, we'll write it as just 1.6 times 10, negative 19. Your voltage, in this case, is 10,000 volts. 10,000 volts. All over the mass of the electron, which is 9.1 times 10 to the negative 31. That gives you, so 1.6 times 10 to the negative 19, 10,000. 9.1 times 10 to the negative 31. Okay, and we get this over here. So we want 2 significant figures, so it would just be 5.9 times 10. So 1, 2, 3, 4, 5, 6, 7. So 7 over here. Nice. The electron next enters the region of a uniform magnetic field. Calculate the radius of the path. Okay, to do that, it's R equals mv over qb. This should be all in your formula sheet, these formulas. So the mass of the electron was 9.1. So 9.1 times 10 to the negative 31. Your velocity, which we just calculated, is 5.9 times 10 to the power of 7 all over Q, which is your charge, which is 1.6 times 10 to the negative 19. Yep, and B. and B is the magnetic field, which is 0.02. 0.02 Tesla. Is that right? Yep. All right, that would give us, so times 1.1 times 10 to the negative 31 over 1.6 times 10 to the negative 19 times 0.02. That gives you, okay, we want it in meters, so what significant figures? Again, just 2, so that'll be 1.7. So 1.7 times 10 to the negative, so 1, 2, negative 2. Is that right? 1, 2, okay, yeah, looks right. Next question. In another part of the particle accelerator, the electrons are deflected by a uniform electrical field as shown in figure 2a. Yep. And by a magnetic field as shown in figure 2b. Explain why the paths of the electron in the two fields have different shapes. Well, that makes sense. Well, remember that this is an electron and it's going to be deflected straight away to the positive. So it's going to be, it's going to attract that positive. So it's like going to run to it. Whereas here, you got to remember that imagine this over here is going at a certain velocity. The electron is going at a certain velocity. Now, you should know by the right-hand slap rule that velocity and the magnetic field are going to give a perpendicular, so a perpendicular magnetic field, a magnetic force, which will act inwards, so inside. So, for example, let's look at this case. Let's say the electron is going straight right now. Let's say your velocity is going straight. If you use the right-hand slap rule, use your left hand, by the way, because this is an electron, and you're going to put your thumb, your fingers are going to be into the page, and what do we see? We see that the palm is at the bottom, meaning that it acts right angle, it acts perpendicular. So if that happens, okay, so now this is your velocity. What's going to happen? It's going to act like this now. So what's happening? It's creating this circular path. So explain what the parts of the electron in the two fields have two different shapes. Well, we can say the force from the electrical field, so this one, field on an electron is always, so it's always the same and pulls the electron downwards, up, downwards. So downwards, so when so let's say when you send an electron into the field, to the field on, so when you send an electron into the magnetic field, it follows a curved, say it follows a curved path that looks like a parabola. Is that true? Yep. So that should give me the marks. That's 2 dot points, if you can see. So that's one over here, and then also one over here. So the force from the electrical field on an electron is always the same and pulls the electron downwards. When you send an electron into the magnetic field, it follows a curved path that looks like a parabola. Due to the, we need to maybe say something else. So we can say due to the velocity, so we can say it follows a curved path that looks like a parallel, but due to the velocity, and due to the velocity and magnetic field being perpendicular, we can say perpendicular, is that how you spell it? Who cares? So being perpendicular to the magnetic force, Okay, is that right? The force from the electric field on the electron is always the same because it's constant and pulls the electron downwards. When you send an electron into the magnetic field, it follows. So when you send an electron in the magnetic field, it follows a curved path that looks like a parallel due to velocity and magnetic field being perpendicular to the magnetic force. Yeah, good. It's alright. I think that should give you it, but not too sure. So question 3, figure 3 shows a DC motor of a square loop of 100 turns and a side length of 5 centimeters and a commutator. The DC motor has a uniform magnetic field of this and a current of this. Okay, what is the force on the side EH when the loop is in position shown in figure 3? Explain your answer. Okay, well, you should see already that we know that the magnetic field lines go from north to south, yeah? And what do we know? Well, the current is going over here, over here, over here, over here, over here, over here, and over here, and coming outwards. What can we see? Well, on the side EH, so over this side EH, we can see that the current is parallel to the magnetic field, which means that the force is 0 on the side. So what do we write? Well, we just write, so 0, and we have to write a explanation. So we can say the force, so the current that runs through the side EH is parallel to the magnetic field lines. And that's it, yeah. So one mark for the answer, and yeah, an explanation. The current that runs through the side line EH parallel to the magnetic field line. Yeah, perfect. Explain the role and the operation of a commutator in a DC motor shown. Okay, so what does a DC motor? You should guys know this, because one way to actually, this kind of question is always common in the exam. Make sure to always have this kind of question, a sample example and a actual sample answer, a very good sample answer, and make sure to have it in your exam, because this kind of question, I've seen it in thousands of exams. So yeah, make sure to have it, and this is gonna, yeah, an easy marks. So we can say, okay, the commutator acts to reverse the direction of the current. Within the coil, so within the coil, every half rotation. So every half rotation at the vertical position. Okay. This reverses the direction of the force on each side of the coil, so that the direction of rotation is constant. All right, that should give you 3 full marks. Yeah. Remember, yeah. So these kind of questions, make sure to have them in your summary sheet. So straight away, you see this question, look at your summary sheet, copy the answer in your summary sheet. That's how you actually, yeah. Make sure you answer every, so explain the role and the operation. Very nice and easy. Figure 4 shows in a sample an AC alternator. Okay, the strength of the magnetic field is 0.5. A loop has 20 turns, the area of the loop is this, and the rate of rotation is 10 Hz. Calculate the average EMF induced as the loop turns from the instant shown in the figure 4 to a point 1/4 of the period later. Show your working and include an appropriate unit. So what we can see right now is that the magnetic flux is at its maximum. So your EMF, so I'm going to look at my summary sheet and look what is the formula for EMF. Okay, perfect. I have it. So EMF is so EMF is equal to negative N change in magnetic flux all over change in T. Okay, 3 marks. So what do we know? Well, we know that the N here, the N value, forget about the negative, but yeah, the N has 20 loops. We know it's 20. Your magnetic flux is just your pretty much magnetic field times your area. So our area here is 0.020 times your magnetic field, so 0.5, all over your change in T. But remember, we want 1/4 of a period. So given that we know the frequency, and we know that frequency is 1 over T, it means that T must equal 1 over F. So if we say, knowing this over here, so it means that your period is just 1 over 10, which is 0.1. So 0.1 seconds, but we must divide it by 4 because we want 1/4 of the period. So divided by 4, we get 1 over 40, which is 0. Blah, 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 this. So we get 0.025. We get this. Okay, so now that gives us, let's check it. So it'll be 20 times 0.02 times 0.5 and given 8 volts. 8 volts. Include the appropriate unit. Yep, this is a very nice question. The AC alternator gradually slows to a stop. On the grid provided below, sketch the voltage output expected. Scalar values are not required on the axis. So, because it starts like, there is no slipping, so because it starts to go, starts slowing down, what's happening is this is how your voltage output should look. It should look like it starts going like this because, and your period should start increasing as, if you look at the formula, negative N. So if you just have a look at this, so your EMF is what? It's 1 over T, change in T, because it's proportional to 1 over T. And it means that if your EMF starts decreasing, because what's happening is that slowing the, it slows down, what's happening? Your change in T is gradually coming up. So your change in period, it starts those periods must start to increase. So this is how the graph should look. So it should start at like a very high, let's say a very high voltage, say like this. And what's happening is gradually it should start slowing down. So like, let's say this is going like that. That's the next one's over here. Okay, but we want the period to a little bit increase. So it's supposed the periods must increase also. So let's say it starts this and then it gets, let's say here. Like that. All right, what am I doing? Okay, let me just nicely sketch this, resketch this. So pretty much just like this. Like this. I want it to be less, so like something like that. So we can see that start to decrease, and the period we want it to start to increase. Okay, perfect. I think that should be enough for this one. Perfect. Yep. we can see that the period, but we want the period to increase. Okay, we want the period to be looking like it's increasing. So let's just try to draw. Okay, so imagine that this is this and that. This is like that and that. And period is like now 3. So let's just draw it. Now what's going to happen is that this period's going to go like that. Yeah, this should be enough. This looks enough, yeah. We can see that the period starts increasing every time. Perfect. An oscilloscope is connected to a sinusoidal AC source whose frequency and voltage output can be varied. Figure 5 shows the trace obtained on the oscilloscope screen, where one horizontal division, okay, represents the time of 20 milliseconds. So one division represents 20 milliseconds, and one vertical division represents 10 volts. So this over here is 10 volts. Okay, that's all right. Calculate the RMS voltage for the signal shown. Okay, well, the voltage is what? Well, it's 10, 20, 30. So 30 volts. So your RMS, so your voltage RMS, is this voltage divided by root 2, which is 30 over root 2, 21. So yeah, just to say just 21. Yeah, 2 signal figures, 21 volts. Calculate the frequency for the signal shown. Well, we know that frequency is what? 1 over period, so which is 1 over t. So the period for this function is what? Well, a whole cycle is here and here. So and there's 4 boxes, so 4 times 2, so 4 times 20 is 80 milliseconds. So this should be 1 over 80 times 10 to the negative 3. Which is 1 over 80 times 10 to the 3. That gives you 12.5 hertz, which is just 13 hertz. Two significant figures. Question 6. Juan conducts an experiment using a shallow tray of water in which waves can be observed. He first produces a straight wave at a frequency of 5 hertz. He measures the wavelength and finds it to be 10 centimeters. Calculate the speed of the wavelength. Okay, be careful here. It's centimeters per second. So what we want to do is, well, we know that the velocity is what? It's frequency times your wavelength. So what do we know? Well, the frequency is 5. Times the wavelength is just 10. So it's 5 times 10. So 50 is your, yeah. Is that right? F times this. Perfect. One now uses 2-point sources producing a wave at the same wavelength, 10 centimeters. So that's a wavelength to investigate 2-point source interference pattern. Okay. He observes lines of maxima and minima in the resultant pattern, as shown in figure 6. The lines on the diagram represent wave crests. Okay. Point P is on a line of minima. Okay, minima. So the nodal line. One measures the distance from X to P, so this to this, to be 16 centimeters. 16 centimeters. Determine the distance from Y to P. Okay, this is not too bad. So, because it's all in centimeters, I'm just going to keep it in centimeters. So, what do we know? Well, we know that path difference is what? It is YP minus XP. Yep. And that's because we also know that this is a minima. So, it's a nodal line. The formula for that is, if I look at my formula sheet, for that one, so it causes destructive interference, so it is n minus half wavelength, so this. Okay, and where does this occur? Well, if you really look at it, over here, so that's 16, but, so this is the first nodal line, so this is one nodal line, and here is 2, but it occurs at the number 2, so we can say, we want to find YP. YP minus, well, XP is what? 16. our n is 2, so 2 minus a half, so what's 3 over 2. And what's your wavelength? It was 10 centimeters, so just 10, because we want in centimeters. So doing this on my calculator gives us, so 3 over 2, 10 plus 16, 31 centimeters. Very nice. One now produces straight waves and places a narrow gap in front of the waves, as shown in figure 7. He next measures the width of the diffraction pattern. So he's measuring these width right over here. So one increases the frequency of the source and explain the effect. So we want to explain the effect that this would have on the diffraction pattern shown in figure 7. So explain the effect that would have on the diffraction pattern. Okay, so if I look at the formula for diffraction, what do I know? Well, if I look over here, okay, diffraction is pretty much, we know that diffraction is pretty much proportional to your wavelength over your width, your gap of that width. What does that mean? Well, one increases the frequency. And what do we know about frequency? If you increase the frequency, so if frequency is increased, it means your wavelength decreases. So what do we know? We can say as wavelength decreases due to frequency increasing, the diffraction pattern, so the diffraction width, we can say, the diffraction pattern width, one increase the frequency, explain the effect this would have on the diffraction pattern. So as the wavelength decreases due to the frequency increasing, the diffraction pattern's width decreases. Okay, wait. As the wavelength decreases due to the frequency increasing, the diffraction pattern will have a low, how would you say it? We'll have a minimal diffraction pattern. But yeah, minimal diffraction pattern. Diffraction pattern with smaller width. So smaller width of diffraction pattern. Is that right? So diffraction is that. So frequency, as the wavelength decreases due to the frequency increase, the diffraction pattern will have a minimal diffraction pattern with smaller width of diffraction pattern. So it makes sense, because imagine just drawing this, and you have what we call these diffraction right over here. These are going in there, and what's going to happen is we've increased the frequency. What's happening, it means that this over here are becoming so close to each other due to the fact, and it means that the actual wavelength starts to decrease. So as it closes there, this is what's going to happen. It's going to start to curve, but it will have only minimal, not too much, because it's going, so we'll only have a minimal. Perfect. Ronnie is conducting an experiment to study the refraction of light. Ronnie passes a beam of light from a laser, from air into a glass slab, as shown, yes. Calculate the refractive index of the glass. Very nice and easy. So it's going to be N1 sine theta 1 plus, equals N2 sine theta 2. So our N1 in this case is air, so it's just 1. So sine, and it's 45 degrees. N2 is what we're trying to find, and sine is 25 degrees relative to the normal line. So N2 is equal to what? So if I go to sine 45, sine 25, that gives me 1 point. We want it in 2 decimal places, so 1.7. 1.7. Nice. So Rani next shines, let me use a different one. So Rani next shines a ray of light from underwater to a water-air interference as shown. Determine the critical angle for the total internal reflection at the water-air interface. So this ray's coming in, you can see. For total reflection, this should be our critical. Our critical angle will give us this perfectly. So it should be, your critical angle should be N1 sine theta C is equal to N2. So our N1 is, well, water, sine theta C. Our N2 in this case is air, because it's going into air. So your theta C is what? The angle is what? So sine inverse of sine 1.33. That gives you let's say 3 decimal places, 48.8 degrees. An angle of incidence is increased. So the angle of incidence is increased to an angle slightly greater than the critical angle. On the diagram provided, draw in a ray or rays that Rani would observe. If you actually increase the incidence more than the angle of reflection, what's going to happen is the thing starts reflecting. It's going to reflect back to the water. So it would look like pretty much like this now. It'd look like something like this. It would reflect back to the water. And yeah, that should be it. So if you increase it slightly, yeah, it should go back to the water. I think that should be the answer. Hope so. List the following bands of the electromagnetic spectrum in order from longest wavelength to the shortest wavelength by writing each corresponding number. Very nice and basic question. Yeah, you should have this in your summary sheet. Well, the shortest wavelength means that the strongest penetrating, so the highest frequency, and the longest wavelength means that the smallest frequency. Well, the smallest frequency from everything is radio waves. So it starts with radio waves. It has to. That's done. And the highest frequency, so the shortest wavelength, is normally gamma rays. But for this one, it doesn't have gamma. So X-rays would be the next one. So, not X-rays, just write that the number. So 6. And we also know the next one is microwaves for this one. If I'm looking at my summary sheet, okay, that'll be 1. Yep. This will be 5, and this will be 4. Is that right? Looks right. Visible light for its ultraviolet, and then X-ray. Perfect. Figure 10 shows the energy level diagram for a hydrogen atom. Okay. An atom of hydrogen is excited to n equals 4. This value over here, so it's over here. And list the possible energies in electrovolts of photons that could be emitted as the atom returns to the ground state. So what can we know? Well, it can go down to here first. It could go down to here. It can also go down to here. What else? Well, it can actually go down to here, which we already have. It can go down to here. It can go down to here. What else? It can also go down to here. Doesn't, yep. Yeah, I think that'll be it. That's the only thing. So these are the only emissions that we can get. So we have 12.8. Well, we'll do the first one. So 12.8 minus 12.1. So 0.7. So first one is 0.7 electrovolts. And so 12.8 minus 10.2, 2.6 electrovolts. 12.8 electrovolts. 12.1 minus 10.2, 1.9. So 1.9 electrovolts. 10.2 electrovolts. And 12.1 electrovolts. Yep, those are the three. Those are the six that we have. Okay, not too bad. A rural town is supplied with electricity from a small hydroelectrical power plant about 20 kilometers from the town. The alternator generates electricity at 500 volts. This is stepped up in a transformer to 50,000 volts. Electricity is transmitted to the town through a 2-wire high voltage transmission line. Okay. This input voltage to the transmission line is at the alternator end and it's 50,000 RMS AC. The current in the line is 15A RMS. At the edge of the town, a transformer converts this voltage to 250 volts AC for the use in the town. The total resistance of the transmission line is 40 ohms. The systems are shown in figure 11. Assume that the transformers are ideal, so no power is lost. Okay, so for this one, well, what can I do? Well, calculate the total power loss in the transmission line. So to make this easier, because this diagram is too much, what I like to do for my students is to make a very basic diagram. So how? Well, we'll know this part here is an alternator. So we'll start with an alternator. Let me just a little bit decrease the size of this pen to this. Okay. Well, we know it starts with an alternator. Nice, an alternator. And what happens is that this alternator, somewhere there, it has a step-up transformer. And this step-up transformer steps up this voltage. Now we're in the transmission lines. And transmission line, we just write it as a resistor. And again, it steps as a step-up transformer. And let's say this over here is like a light, which is the townhouse. And let's write the stuff. So we know over here, we have 50,000 volts on RMS. And we know this one over here was 5,000. This was 5,000 volts. This one's 40 ohms. This over here, the current is 15 amps RMS. What else? The transformer converts the voltage to 250. So here, the voltage that comes out is 250 volts. Okay, that's all we need. So let's try to calculate this one. So let me just put the thing back. Okay. Having this diagram is going to be helpful. Calculate the total power loss in the transmission line. Okay, this is not too bad. So we know if I'm going to look at my summary sheet, formula for power. That is over here. Power, P, is equal to I squared over R. So your power loss, so P loss, is your current that's running through the resistor, which was 15 amps. 15 squared, your resistance, which is 40. That would equal, so 15 squared times 40, that's 9,000 watts. So 9,000 watts. What is the smallest significant figures? It's just 2. So we can just write this as 9.0. 9.0 times 10 to the power of 3. Very nice. Calculate the voltage. I'm just going to take this diagram, copy it. I'm just going to copy this and I'm going to put it over here to calculate this one over here. So it says calculate the voltage input from the transmission line to the step down transformer at the end of the line. So we want to calculate the input, which is over here. So calculate the voltage input from the transmission line to the step-down transformer at the end of the line. Okay, so we want to calculate input here. Well, we know that the overall is 50,000 at that point. So let's calculate the voltage of the resistor. So voltage for the resistor, oh no, for the transmission, that's right, because it's a transmission line. Transmission, so just say call it transmission line, so TR, we call it. So transmission line, so TL is equal to, by Ohm's law it is, the formula is current times resistance. So VTL is, the current was 15, the resistance here was 40, which gives us 15 times 40, 600 volts. Now, the total voltage is 50,000 that was given. We want to minus 600, and that would give us the voltage input. So your VIN is equal to what? 50,000 minus answer 4940 volts. So we want this to two significant figures. That will be 4.9 times 10 to the power, so 1, 2, 3, 4, power 4. Explain why AC rather than DC is generally used for long-distance power transmission. Include the steps involved in the process of long-distance power transmission. Okay, this is such a recurrent question. So this is like a common exam question. And I would suggest for most students to put this like a sample, like an answer to this. So the answer for this one is, okay, we know that transformers only operate with AC voltage. So generally that's why they don't use. And also we can talk about, okay, what can we say? Well, let's talk about, okay, transformers. We can say that transformers only operate with AC voltage. Okay, that should give a mark. And also we know they they allow the voltage to be stepped up to high values with minimal loss of power, because they are ideal, and at the same time the output current, we can say output, so output current is reduced by a similar ratio, which would make sense. I mean, it makes sense, absolutely. It's being stepped up. So if you don't know that, okay, this is a step-up transformer. So this is, let's say it's 1 to 10. So it steps up the voltage. What do we know? Well, this is the formula. Well, it's like, well, how would I say? Let's say this is your, so the ratio, look at the ratio. So V1 to V2 and is equal to I2 to I1. So what's happening? Well, if you increase, if you want to increase this voltage, your output voltage, is that the formula? Just let me have a look at this. Is that the formula? Yeah. So what we want to do is, let's say if we wanted to increase the output voltage, so this voltage over here, what would we normally do is we step it up. But the problem is, if we step it up, the thing that will come, so like this is our output voltage, the current will become smaller because it's inversely proportional. So that's what this means. That's what we're saying here. It's similar ratio, but it's reduced because it's inversely proportional. Yep. And we can say, what can we say? Well, the reduced current in the transmission line lines means that there is, so that the power loss is much reduced. It's much smaller. Let's say smaller. So it's much smaller, as we know, as power loss is proportional. Is proportional to the current squared. To the current squared. And that's true, remember. This over here. Power loss is current and it's been squared. So yeah, that's true. What else can we say? Say that the voltage, at the end of the transmission line lines is much closer to the output voltage from the step up. So step up transformer. So at the end of the transmission line, the voltage is stepped back down to the domestic supply, to the domestic voltage supply. So domestic voltage supply. That should give you the 3 marks. That's a long answer, but yeah, you should give your answers in dot points, but yeah, this should give everything. You can pick up points from this and put them in your summary sheet. Yeah, so that's that for this question. Looks all right. Some students conduct an experiment using 2 trolleys A and B of mass 6 kilograms and 2 kilograms respectively. So in the experiment, trolley A is moving at 2 meters per second and trolley B is stationary. Before they collide, there is a spring between the 2 trolleys attached to trolley B. Okay, so there is a spring. When the trolleys collide, they compress the spring and then move apart. After the collision, trolley A is moving at 1 meter per second. The experimental setup shown in figure 12. Ignore the mass of the spring. Calculate the speed of trolley B immediately after the collision. Well, we don't have to worry about the spring in this case due to the fact that, yes, it will transform some of the energy, kinetic energy to, spring potential energy, but it will again bring it back. So it will pass it back to all kinetic energy. So we can just, So what can we say? Calculate the speed of the trolley. So the momentums are the same anyway. So what can we say? Well, we can say M, A for the first one, and U, same one, plus M, B, U2 must equal to MA, V1 plus MBV2. Yep, because they are separated. So the mass is 6, your initial velocity is 2, plus your mass for the other one's 2, but it's at 0. So we can just cancel this all out. Oops, we can just cancel this all out. Must equal to your mass, which is 6, 1, plus 2, and we want to find V2. So your V2 is actually equal to 6 meters per second. Very nice. Determine whether the collision is elastic or inelastic. Very common question. So to do that is we want to look after this condition. Is the before kinetic energy equal to the after kinetic energy? Let's check. Well, before kinetic energy is what? Well, it's half your mass of the first one, which is 6. Velocity was 2 squared, plus half the mass of the second. Velocity is 0 squared, so it's just 0. So overall, this one is 3 times 4. Yep, 4, 8, 12, so that'll be 12 joules. Your after kinetic energy is half 6, 1 squared plus half 2. Well, we already calculated, which was 6 squared. So it's 3 plus 12. What have I done here? Wait. That's okay. This is what okay. What have I done here? What have I done? I've done something wrong. So if that's 12 minus 6, that's 6. And we have to divide it by 2. So this is supposed to be 3. Oh, stupid, yeah. So that's 3. This one over here should be 3 squared, which is 9 plus 9, which is 12 joules. Because they are equal, your before kinetic energy is equal to your after kinetic energy. Collision is elastic. Alright, a pair of students, Pat and Alex, discuss how the kinetic energy of the system would vary with time. Pat's opinion is that the variation would be represented by the graph in figure 13a. Okay, and Alex's opinion is that the variation would be represented by the graph in figure thing. So, who's correct? Well, that's kinetic energy, the system. Well, Pat is right. It's because, remember, there is a spring. Now, if there was no spring, yes, Alex is right. It is constant throughout the whole thing, your kinetic energy. But because Pat, there was a spring. So when they collided and the spring compressed, some of that kinetic energy transformed to transfer to actual spring potential energy, elastic potential energy. So that's why there should be some loss. And again, it gradually, after they kind of get off as the spring, like it recompresses, the kinetic energy is back transformed into kinetic energy, and that's why you see it goes up again to its normal state. So what can we say? What would you say? Pat is correct. We say, what do we say? Well, we say the temporary loss of kinetic energy, let's just say EK, was stored in the elastic, was stored as elastic potential energy, was stored as elastic, elastic spring potential. Energy. Alright. That's for that. Looks like the next question. So figure 14a shows a model of a car of mass 5 kilograms moving in a part of a vertical circle of radius 4 meters. At the lowest point L, the car is moving at 5 meters per second. Figure 14b shows that the model car is at its lowest point at L. Okay. On figure 4, draw the arrow to show the resultant force on the car. Okay, now you guys should know, if there's this circular, we should know straight away that there would be a centripetal force that goes towards the center, which is right over here. And this is what I just call FC, your centripetal force. Draw an arrow to draw the resultant force. Yes, so your resultant force is your centripetal force. Calculate the normal reaction force of of the track on the car at L. Alright, to do that, well, what do we know? Well, if we look at this figure, what do we know? Well, I just take a screenshot of this. Just take a screenshot of this and look at it over here. Alright. So, bring it over here and let's really look at it. So, allow paste. Okay. Let's just do some diagrams here. Well, what can we see? Well, this resultant force, there's going to be the electron may pass. Oop, what was that? Okay. So what's going to happen? Well, we have a force of gravity, which is we call mg. We also have the normal reaction force, so this is the normal reaction force that will occur, so your N, your normal reaction force. And these are the two. And there is also that force of centripetal. So these are your three forces that are acting on the car. So knowing that, if we add them all together, let's add them all together. So N plus N, because remember, we're taking the upwards as positive. So N plus FC plus but minus mg must equal 0. That is your actual overall force, because the car's at rest. Now there's no force actually acting on it, so at that point is 0, no acceleration. So you're okay. Well, we want to find N. So N is what? FC plus mg. And we know that FC is what? mv squared over r plus mg. So what's that? Well, your mass of the car is what? 5. Your velocity of the car is 5 squared over your radius, which is 4 squared. No, just 4 plus 5. Your g is 9.8. Doing all of this should give you what? So 5 squared, 4 plus 5, 9.8. That gives you a total answer of 80.25. So, but to what significant figures? 3. So, 80.3. 80.3. So, a stone of mass 20 kilograms is thrown from the top of a 15-meter height above the sea at an angle of 30 degrees to the horizontal and at an initial speed of 20 meters per second, as shown in figure 15. Ignore air resistance. Calculate the kinetic energy of the stone immediately after it strikes the sea. So we want to calculate this. So the velocity, we want to, so there'll be some velocity that will be acting. And this velocity will have this. Okay, let me just make this nicer. So, alright, if I make this smaller, like that. Okay, so there will be this and this. Okay, something like this. Well, this is your velocity, because remember, your velocity is not just a velocity, it's a component of velocities. And this is what velocity we want. To get that velocity, well, we know that this over here is going to be constant. This over here, this velocity, your horizontal velocity, which is what? Well, it is just 20 cos 30 degrees. Yep. What about the other one? Well, the other one we have to calculate, because remember, it changes. It's not constant as like the horizontal, due to the fact that vertically we have acceleration, which is 9.8. So there is, yeah, we have to take in that consideration. So let's look at it. Well, okay, so we want to calculate the velocity. So v, final velocity. Well, we know u, your initial velocity is what? It's just 20 sine 30 degrees. What else? Well, we know s is negative 15. And we know acceleration is negative 9.8. So knowing these, So using your SUVA, it's v squared equals u squared plus 2as. So your v is what? It's 20 sine 30 degrees squared plus 2. Let me just take that, put it over here. 2, 9.8. S is negative 15, which your velocity is, if I do that in my calculator, so 20 sine 30 squared. Okay, so 30 squared plus 2, negative 9.8, negative 15. That gives us 19.8. So this one's supposed to be like 19.85, somewhere around that. So we know these two, and if we find the actual square root, like the using Pythagoras theorem to find velocity, let me bring it back to the original. Now we know this, so we can say velocity is equal to the 20 cos 30 degrees squared plus 19.85 squared, which is 20 cos 30 squared, which is 26.34 meters per second. Now your kinetic energy is half your mass, which is 2, velocity squared, so 26.34 squared, which is this velocity being squared 694. So 694, that's that. Let's just write 694 here. 694 joules. Is it, to be honest, I want to write it in okay, two significant figures, so 6, let's write it as 6.9. 6.9 times 10 to the power of 1 to the power of 2 joules. Some students test a spring to determine the spring constant K. The experimental setup is shown in figure 16. Okay, so there's an unstretched spring, and they put some masses added, and springs. 0.5 kilogram masses are successfully added to the end of the spring, and the resulting length of the spring was measured each time. The results are shown in the table below. Record the data from the table as a graph on the grid below. Include labels, scales, and units on each axis. Given that these measurements were taken with a meter ruler, graduated to 5 centimeters interval, and held by hand. Insert a realistic uncertainty bars or error bars. Draw a line of best fit. So that's 5 marks. Okay. Well, let's look at this. So what we do is we add masses. So this is going to be your x. So this is going to be your actual independent variable. Yeah. Independent variable. And the length of the spring is what's going to happen, change. So like when you add more masses, what's going to be affected? Your y values, which are your dependent variables. So your masses is going to be your actual x-axis. So if I just draw a nice something like that, and we can something like that, and say this is that. Okay, and let's say this is your mass, so m in kilograms, and the other one's in length. So length we'll make in meters. Makes it easier for calculations. Okay. We have 5 out of these mass. So we'll have, let's say this one We'll have 0 mass added. We'll have 0.5, 1, 1.5, 2, 2.5. So we have those, perfect. The length of the spring, so it's probably the best if we go by, let's say 2s. Is that right? Because it's much smaller. So if we go by 2s, let's try that. So 2, 4, 6, 8, 10. Do you think that'll be enough? Let's do 5s. Let's try to do maybe 5s in like. So this is your. Okay, how do we do this? So this is 5. This is 10. This is 15. This is 20. This is 25. 25, 30, 35, 40, 45, 50, 55, 60, 65, 70. Perfect. Okay, if we're going, it means if we're going by 5, then, well, it's not meters then. It's just, well, we have to then say it's centimeters. We'll have to make this into centimeters. Okay, so we have that. Okay. And then let's start just drawing points. So let's just put some points. So we have the first point, 0, 40. So 0, 40, right? Let's use different color. So 40 right over there. Next one, we have 45 and 0.5. So 0.45. So that will mean we're going 45 right over here. 53 for the next one. So 53, which is just say over here. 57. So 57, that will be right over here. 63. So 63 would be close to over here. 70. The other one's 70, so right over here. So that's good. What else? Well, record the data on the grid, include labeled scales. Yes, on each axis. Given that these measurements were taken on a meter ruler, graduate to 5 centimeter intervals. So 5 centimeter intervals. And held by hand. Insert a realistic uncertainty. Okay, so the length has uncertainty. And so because it's 5 centimeters, it means that graduated to 5 centimeter intervals. Half of that, so half of 5 is 2.5. So 2.5 centimeters is going to be our actual error bars. So, which is like likely over here. Let's close to likely this. Our error bars are going to look like this. 2.5, let's say, yeah, like 2.5 up there and 2.5 up down. Okay, perfect. So, yeah, so it looks like this. Something like that, okay. And let's draw a line of best fit. Well, you must try to pass through all of them. So let's just draw a nice line. Perfect. So it does pass through all of them. So that's a nice line. Record the data on the graph. Include labels, units on each axis, given that these measurements are taken from a meter ruler. Graduated to this. Held by hand. Insert realistic uncertainty bars or errors. Drawn the best line fit. Okay, this looks nice. Yeah. Next question. So from the graph in part A, determine the spring constant K of the spring and include a possible uncertainty to your value. Okay, so we know K is F over X. So what does that mean? Well, we know the force is just mg, mg, due to the fact that it's been hanging down. It's a down, mg. So, and we know that this, if we find the actual gradient of this, it will give us x over m. So our gradient of this line will give us x over m. Okay, so let's try to find 2 points. Let's say 2 nice points. Well, here's a nice point right over here, and here's a nice point over here. What are these points? Well, this point over here is, do it down. So this says 0.5 divided by 3. So that point is 0.5 plus this. So it's 0.66. Yep. 47.5. This one over here is so 0.5 divided by 3. Get this, so it'll be 2.5 minus that. So this one over here is 2.33 67.5. Okay, we got these two values, so let's do it. So what we're going to do is, that is saying 67.5 minus 44, so 47.5. But we want to, remember it's in centimeters, but we want to make it to meters. So times 10 to the negative 2 all over 2.33 minus 0.66. So this would give us 67.5 minus 47.5 to the negative 2. 2.33 minus 0.66. Okay. Into the power of 2. That's giving us 0.1197, blah, blah, blah. And so submitting into this equation, so we just have to flip it. So 1 over, so to get m over this, so to get this, it'll be, we just take this, move it smaller, and so we, what are 3 marks for that? Okay, so to get that, it's 1 over 0.1197 multiplied by g, which is 9.8. That gives you your k value. So 1 over this answer times 9.8. That gives you 81.83. So 82. So k is 82. Okay, but then it says, okay, include a possible uncertainty in your value. Okay. This is a stupid question. Uncertainty, if it's graduated to 5 centimeters. Okay, so if it was 5 centimeters and we halved it, which was, we said 2.5 centimeters. And then it just, it should become 3. Like, it wouldn't affect the x variable. It's just, okay, so we have that. Okay, we have that, and times 10 to the negative 2. So your uncertainty, which it should be because it's it was that, and we multiply, it should be 3. It's 2.5, but rounding it up, it's 3. So we can say plus or negative 3. Look, by the way, this is not an actual real answer, by the way. Not an actual answer. Like, it's not exactly the answer. It's a close approximation of the answer due to the fact that you have to draw it and see if the best line fit. But yeah, it should be close to it. Newton per meter. Is that right? I'm not too sure of the uncertainty. Like, I'm sure the 82 makes sense, but the uncertainty is just confusing me. It's 5 centimeters and we half that, because so that'll be 2.5 centimeters, and then that means close to 3 centimeters, but there's 3 centimeters, yeah. Then it wouldn't be affected. Yeah, I'm not too sure about this one. I'll have a look at the answer. Oh, there is no answers to this, so yeah, these are just suggested solutions. So yeah, we'll move on to the next question. All 5 masses are added to the end of the spring, and the spring is then released to a 40 centimeter position and released. Calculate how far the spring stretches below its initial rest position. Okay, this is not too bad. So all 5 masses are added to the spring. So your M is 2.5 kilograms. The spring is then raised to 40 centimeter position, so back to its original position, the 40 centimeter, yep. The spring is raised to the 40 position and then released, so when it's released, explain how far the spring stretches below its initial rest position. Okay, this is not too bad. So when it's initially on top of here, what do we have? Well, the only thing it has is what? MGH. It has only potential, gravitational potential energy at this point. So MGH is at its maximum. But when it springs down here, what's happened is that all of this is changed to half kx squared to spring potential energy. So equating both of these, so MGH, well, our H value is just K. So we're saying MGH, which is, our H is X, equals half kx squared. Half kx squared. So, and we want to find x. So, what do we do? Well, if we move this side, minus mgx equals 0, and we take x as a common factor, okay, so x, half kx and minus mg, well, x is 0, and this half equals, so it'll be half kx minus mg must equal 0. So that's, yeah. So summing all the values in, so we know it's half, your k here is, let's just say 82. Your x is what we're trying to find, should equal to mg, or 2.5, 9.8. So your x value is 2.5 times 9.8 divided by 41. 0.597. So how far the spring has changed is 0.597 meters. But we want it in centimeters, so so we want to divide it, so wait, to centimeters, we want to times it by 100. So it'll be 59.7, so just 60. Yeah, we want to, yeah, just 2, okay, so it'd just be 60 centimeters. So it's 59, and it changes to 60. Muons are elementary particles created in the upper atmosphere by cosmic rays. They are unstable and decay with a half-life of 2.2 microseconds when measured at rest. That means that in the reference frame of the muons, half of them decay in each time interval of 2.2 microseconds. In an experiment, muons with a velocity of this were observed by some scientists to pass the top of the mountain of height 2,627 meters, as shown. The scientists measured the number of these worms reaching ground level. Okay. Calculate the half-life of worms as measured by the stationary observer on the ground. So, perfect. So this case is very basic. So, what's found is that muons, this is the really story of muons. Muons are actually these elementary particles, and they, in reality, their half-time makes them they should never actually touch the ground. But for some reason, they still reach the ground. And how is that? Well, because it all depends on the stationary, like the frame of reference. So for us, imagine we're scientists and we're watching this mountain, and this muon's going down at a speed, and we're watching it, and what's happening is, what's happened to me? Wait. So, what's happened is that for us, when we're looking at it, time pretty much. Wait. What has happened to me? Okay, so what happened to me? Okay, I know the story. So it was T to Y. So it means that time dilates. Okay, so what happened was that these muons were just hitting the ground when they were not supposed to. But they found that in the reference frame of the scientists, that us scientists, when we look at them, they're actually hitting the ground. It's because of the time dilation. There's actually a factor, and that factor is this gamma here, which is 10. So the time is actually dilating, so it's actually slowing down, and that's why they're reaching and hitting the ground, which is kind of beautiful actually, if you really look at it. So that's the calculate the half time of the muons and measured by the stationary observer on the ground. So if we're measuring them, we know that time will dilate when we look at it. So we can use that formula. So we can say T proper time this, which our actual T is 2.2 times 10 to the negative 6 times 10. So it dilates by a factor of 10. So T equals 2.2 times 10 to the 6 times 10. That gives you 2.2 times 10. So 1, 2, 3, 4, 5. So negative 5. Negative 5. So that will be 2.2 times 10 to the negative 5 seconds. Okay. From their frame of reference, the muons see the ground rushing upwards at a speed of this. Find the height of the mountain as measured by the muon. So the muons, when they're falling, they're actually experiencing what we call is length contraction. So that length, the length is contracting. So we know the formula for length contraction is L, proper L over this. So it means that 2627 over 10, because length is contracting, so it's becoming smaller. So that's what. So if we're dilating this and dividing this by that, that gives us a final answer of 2627 meters. Yeah, meters. Okay, so doing this, so this is just 263. Simplifying it. Explain why many more muons reach the ground than would be expected according to classical physics. This is what I want to explain. Okay, this is the best way to explain it. So, let's write. So 2 marks. Let's say. So in the scientist's reference frame, the muons move towards the ground, at a speed of 0.995 C. So the half-life of the muons is dilated by a factor of 10 when observed. So when observed by stationary scientists. Stationary scientists on the ground. Okay, that is that. And what else do we want to say? Faster than what you observed in stationary. That's why many muons reach the ground. Okay, so we can say that's why many muons reach the ground. No, actually. No, let's not write that. Let's move on to the next one, which is so in the muons frame of reference. So in the muons frame of reference. So reference frame. That's just right. Yeah, reference frame. Reference frame. So reference frame. The ground moves towards the ground moves towards the muons at a speed of 0.995 C. The distance is contracted by 1/10 of 262.62627 meters when measured by the muons, and thus the arrival time of the ground is reduced by a factor of 1/10. Yeah, so that's that. I think that should give you the 2 marks. It's a lot that I've written, but yeah, you can pretty much take those and put them in your summary sheet if you need. All right. Question 17. Some students study the diffraction of electrons by crystal lattice, and the apparatus is shown in figure 18a. In this apparatus, electrons of mass this accelerate at the speed of this. The electrons pass through the crystal and the diffraction pattern is observed as a fluorescent screen. The pattern that the students observe is shown. Okay. Calculate the Broglie wavelength of the electron. Show you're working out. So if I'm going to look at my summary sheet, the Broglie wavelength, which would be over here. So, okay, to find the Broglie wavelength, what I'm going to need to do is, Broglie wavelength is h over p. So, the momentum is what? P equals mv. So, your mass is 9.1 times 10 to the negative 31, and your velocity is 1.0 times 10 to the power 7. So your P for this is 9.1 to the negative 31, 1.5 times 10 to the power 7. We get that. So 1.365 times 10 to the power negative 23. And we say that, okay, so this, I just want to make it smaller so I can put everything together. Just put it over here, put this over here, take this overall, put it right like over here. It's nice over here. So we can say that this is, H is what? Well, H is, should be in your formula sheet. So it is 6.63 times 10 to the negative 34 all over 1.365 times 10 to the negative 23. So doing this, let's check what we get. So so we get 6.63 times to the negative 34. And so, okay, we get 4.85 blah blah blah. So we get, okay, we get wavelength is equal to 4.85 times 10 to the negative 11. So we want it in nanometers. So if I multiply, okay, nanometers, so what I'm going to do is, if I multiply 10 to the power of, to make it to negative 9, what we're going to need is power of 2. So yeah, 11, 10, yep, so divided by power of 2. And that will make it to 4, so it will become 4 point, yeah, so 4.85. So 4.85. What's this? 4.85. So 4.85. I don't know what's happened to me. Wait. So we want it in nanometers. Okay. What am I doing? Okay, I got it. Okay. So this 4.85. So 4.85 to the negative 11 divided by 10 to the power of 9. Yeah, negative 9, which gives you, let me just take that off. So what is the all in two significant figures? So 4.9 times 10, so it'll be 1, 2, negative 2. Yep, so that. Nice. The students next increase the accelerating voltage and hence the speed of the electron. Describe the change to the pattern that will change. So describe the change to the pattern that they will observe and give you a reasoning. So if I look at my summary sheet, all right, so what can we see? Well, they increase the speed. It means that, okay, because, well, what do we know? Well, that this is P H over P, and P is mv. Your momentum is just mv. So if we're increasing the velocity, we're decreasing. So if velocity increases, your wavelength decreases. So if your wavelength decreases, this thing becomes like the wavelength, the crests will become smaller. So describe the change to the pattern that they'll observe and give you a reasoning. Okay, we can say as velocity increases, wavelength decreases. Okay, that should give you 1. As well as decrease wavelength. Therefore, let's say, therefore, the width, I think, of the crest will decrease. As your next increase the accelerating voltage and enhance speed, describe the change the pattern and they'll observe. So as the velocity increases, the wavelength decreases, therefore the width of the crest will decrease, making the pattern look smaller. Making the pattern look smaller. I think that's that. I'm not too sure actually. Yeah, but I know like it decreases, but I don't know how to write it. Wait, as the velocity increases, wavelength decreases. Therefore, the width of the crests will decrease, making the pattern look smaller. Okay, that's enough. The students replace the electron source with an X-ray source and find that the pattern on the screen is similarly shaped, so the wavelength is the same and spaced to the pattern observed when the electrons were at the original speed at this. Calculate the energy of a photon from the X-ray source. Give you an answer to that. Very nice and easy. Alright, so energy of a photon is hc over this. Well, we know h in this case. Oh, we want an electrovolt, so our h in this case will be 4.14 times 10 to the negative 15. Your c value, which is the speed, the original speed is still 1.5, so 1.50 times 10 to the power 7 all over. Wait. Oh, wait. The students replace the electron with this and find the pattern of the stream. Say, the electrons. Okay, no. So just the speed's c, by the way, because it's photons. They're not actually electrons. Yeah. So it's 3.0 times 10 to the power of 8 all over your wavelength, which is the same, which was 4.85 times 10 to the negative 11. Yeah. Yep. So doing this, so it's that times 3.0 times to the power of 18, 4.85 times 10 to the negative 11. That gives us this. So it gives us 25608 electrovolts. We want to 3 decimal places, so that will be 256. So 2.56 times 10 to the power of 1, 2, 3, 4, power of 4. Question 17. Some students set up the apparatus shown in figure 19 to study the photoelectrical effect. In particular, the relationship between the frequency and the intensity of incoming light and the maximum kinetic energy of the emitted photoelectron. Assume that all filters give the light the same intensity. The apparatus consists of a source of white light, a set of filters, each of which allows only light of a selected wavelength to pass through, a photocell consisting of a metal plate and a collector electrode enclosed in an evacuated no air glass, a case, a voltmeter V, an ammeter A, a variable DC voltage source, and with a particular filter in place and the same light source, the students gradually increase the voltage as measured by the voltmeter from 0. They plot the current measured by the ammeter as a function of the voltage measured by the voltmeter. This is shown. Explain why the current drops. Well, it makes sense because the voltage is slowing down the movement of the photoelectrons towards the collector electrode. So the more the voltage goes up, the more photoelectrons that will start to be prevented to reach that collector. So it means at the voltage X, where the photoelectrons are all blocked, and this pretty much means that current must therefore become 0 because there's no more photoelectrons. So we can just have to say that. Let's write that. Okay, so the voltage is slowing down the movement of photoelectrons towards the collector electrode. So as voltage goes up, more and more, the photoelectrons, more of the photoelectrons are being prevented from reaching the collector. So when we reach point X, all the photoelectrons are blocked. So are blocked. And current stops completely. That's that. Okay. The students next use 5 filters to give 5 frequencies of light falling on a metal plate and measure the stopping voltage on the voltmeter for each frequency. The data collected is shown. So the stopping voltage is what? Just the key, the K max anyway. So it's similar to the K max, but it's in electrovolts. Remember that, guys. So frequency, plot the data given in the table above on the axis provided below, then draw a line of best fit to show the maximum kinetic energy of the emitted photoelectrons versus the frequency of light falling on the metal plate. Okay, so very easy. So what we're going to do is, well, the first one is 4.5. 4.5 and 1.3. So 1.5 is here. So 4.5 is here and 1.3. So 1, 2, 3. So here, right over here. The next one is 5. And it's 1.5. Right over here. Next one is 6.1. So 6.1. So that's 6.5. So say 6.1 is over here. And that 2. Right over here. Next one is 6.7. So around 7. 6.9. 2.5. Right over here. And 7.6 to 2.8. So 6, 7, 8, right over here. Okay. So anything else do we need to know? So if I just draw a nice straight line, perfect. Straight line, done. Yeah, so that's it. From the graph plot in Part B, determine the value of Planck's constant, h, that the student would have obtained. Give your answers correctly to significant figures. Very nice and easy. So it's the gradient. Okay, so let's pick 2 nice. Okay, so what are some nice values here? Let's say this point over here. And also this point over here. These are 2 nice points, so that goes over here. The other one goes over here. So the first point, let's say, is what? So it's 2.6. So 2.6 minus, and it's going to be divided, blah, blah, blah. And it's going to, the other value is 7.5 minus. Okay, that's good. So now let's try the other value too. So the other value is this over here, 6, and right over there. So 6, the other value is 2. And remember, times 10 to the negative, so 14. That's equal to, let's rub that out. Okay, so 2.6 minus 2, 7.5 minus 6 times 10 to the power of 14. That gives you 4 to the power, so 4 times 10 to the power of negative 15. To 2 significant figures, that's going to be 4.0 times 10 to the negative 15. Done. For this particular experiment, identify each of the following. Yes, you need to know this, by the way. So, in the formula sheet, you should know what are the dependent variables and independent variables for the experiment of the photoelectrical effect. So, one of the dependent variables that I'm going to say is the maximum EK. So, your maximum EK of ejected electrons. Ejected electrons, that's one. And one of your independent variable is the frequency of the incident light. Frequency of incident light. Alright, that's that. Let's look at the next one. For this particular experiment, identify one important control variable and indicate why this is a variable should be controlled. One control variable in this experiment is the intensity of the light. So we can say intensity of light. So the goal, and why is that? So the goal is to study, so the goal of actually, like the overall goal of the photoelectrical is to study how the maximum kinetic energy of photoelectrons change with the frequency of light that releases those electrons. So we need to pretty much to attain, like to make sure we get accurate results, we need to stay we need to maintain consistency by keeping other variables constant. That's what we need. So think about this variable should be intensity of light. The goal is, we can say the goal is to measure maximum KE of photo electrons with frequency of light to attain, we can say attain accurate results. So to attain to accurate result, we need to maintain consistency. So we can say we need to maintain consistency by keeping other variables, by keeping all other variables, variables consistent. Okay, that's that. I think that should be enough. Students performing the photoelectrical experiment on a different metal have carefully determined the uncertainty in their measured value for the maximum kinetic energy of the emitted photoelectron. Then this is represented by the uncertainty bar and the error bar drawn on one of the data points on the graph below. The uncertainty in the values for the frequencies may be neglected. Okay. On the graph above, show the steps needed to determine whether the data points may be fitted by a straight line. Okay, so for it to be fitted by a straight line, so let's make first, we need to make sure we have similar distance, like the error bars need to be looking the same. So let's say this error bar is like that. This one should be like that around. This one's around like this. This one's around like this. So if I'm going to draw a straight line, it must pass through all of them. And it does. So that's good. So what can we say? Well, okay, the first step we can say is draw the same, not distance, draw the same, we want to draw this like the same actual level, like the same of the error bars. We want to draw the same, I don't know, let's say draw the same distance if each error bar. So I draw the same distance of each error. I don't know. How do we write this? Draw an error bar. Let's say draw an error. Let's say we'll say draw an error bar. So draw an so let's say draw an error bar that is similar in size, oh my god, similar in size, draw an error bar that is similar to size of the first one, for all. Okay, then draw a straight line, a straight line. If the line passes through all the points, through all the error bars, then a straight line can be drawn, as shown. Let's say as shown. That's it. I should need 3 marks. How long, man? This is such a... Okay, we're nearly done. Alan Young double splits experiment. Explain the implications of this experiment for the understanding. Okay, this should be in your summary sheet. I've made sure everyone in my tutoring class has these kind of questions because they always repeat every year. So have these kind of questions. So if you look at your summary sheet, I'm looking at my summary sheet right now. I'm just going to write these dot points. That's what I'm going to do. So what Young did, it says outline why Young. So Young passed a single color beam of light through a single slit, and then through a pair of closely spaced slits. Okay, that's one. So another one is he observed a pattern of alternating bright and dark bands. So bright and dark bands on the screen. This pattern known as interference pattern results from the interaction of two light beams, each originating from one slit. This phenomenon is caused by wave interference. Done. Another 3 mark. Explain how a single photon Young double slit experiment can be used as of the dual nature of light. Okay. So for this one, when we can say it's in a summary sheet. So if you guys have my summary sheet, my tutoring class, if you have my summary sheet, it has a similar question like this. So this is how we can pretty much show evidence of the dual nature of light. So this is what you should write these. So if I'm looking at my summary sheet, when very just a single photon goes through the double slit setup, one might predict it would pass through one slit, resulting in two bright bands on the screen. Surprisingly, a pattern of alternating so alternating bright and dark bands. Bright and dark bands emerge. So emerges over. So very emerges over time. This outcome suggests that even a single photon displays wave-like behavior. Wave-like behavior. Thus, the experiment provided evidence. It provides evidence for the dual nature of light. Okay. Let's go. 5 marks for the last question. Wow. So what does it say? It says, outline the conclusions that the nature of light that Albert Einstein made from the observations of the photoelectrical experiments. Include how these conclusions arose from the experimental observations and why these conclusions contradicted the simple wave. Okay, I have a similar question to like this in my summary sheet. So let's try to use some points from that to get some marks. So 5 marks is a lot. So what I'm looking at it. Okay, so looking at the summary sheet, we can see that Einstein discovered that photoelectrons increase with light intensity. So with light intensity and the maximum kinetic energy of photoelectrons is determined by the light frequency. Say that. So higher in light intensity, higher light intensity leads to more photons, in the beam, increasing interactions with metal electrons and greater photoelectron production. Okay. So each photon in a single frequency light beam carries a fixed amount of energy, So when the electron interact with a photon, it can gain So gain a partial or complete energy. Oh my god, this question. Which overcomes the metal's work function. Okay, and escapes as a photo electron. So surface electrons absorb the full energy, resulting in maximum kinetic energy. All right, emission. So Einstein's conclusion contradicted the simple wave model. Yep, so a simple wave model. Okay, which suggested a high intensity light would yield higher energy photoelectrons. And that the light frequency would not impact the emitted electron energy. So energy. All right, that's that. Yeah, so look, this over here is a full explanation, by the way. This is from my actual, my notes. Yeah, so you can pretty much, to learn, guys, please have a read through this. Take the main important parts of how Einstein actually contradicted the simple wave model and how his theory didn't work. So make sure to take some points that I put over here. This is probably like the most, like a 5 marker, but no one writes this. Make sure examiners like dot points, and that's what we like. So make sure to put dot points, yeah? Make sure to put dot points in your answers. So yeah, have a read through this. Take some information. For example, I don't look, this is too much writing, so read this, take the important part and make them to dot points. And this is the key. Put them in your formula sheet because these kind of questions are always similar in the exams. So yeah, I hope you guys enjoyed this video. Make sure to like and subscribe and share this with your friends. You know, guys, support each other. And yeah, I hope you guys do well this year for physics. You know, physics, so I do tutoring, private tutoring. I do specialist methods, physics and chemistry. If you guys want that, please, my link so my email will be linked in the description. And yeah, you can pretty much email me there and we can have a discussion. And yeah, guys, I hope you guys enjoyed this video. And it was a long video, to be honest. I'm very tired right now, so I'm probably going to sleep after this. And yeah, I hope you guys enjoyed and have a good day. Take care.